Question 2, these questions are about electrical conduction and the force of a conductor in a magnetic field. So question A, the diagram below shows a copper rod inside which an electric field of strength E is maintained by connecting the copper rod in series with a cell. Connections to the cell are not shown. So you've got this electron here and you've got your electric field in that direction. On the diagram, draw an arrow to show the direction of the force on the conduction electron shown. Label this arrow with the letter F. So the arrows on your electric field always show the direction that a positive charge would take. So because this is an electron, it would go in the opposite direction. So you would have something like that. Then it says, describe how the electric field enables the conduction electrons to have a drift velocity in the direction shown along the copper rod. Well, because we have this formula over here, that E is equal to F over Q, we can therefore have that F is equal to EQ. So the electric field will cause a force to be applied to the electron, and the force will be in that direction there on this electron. So the electron will accelerate due to the force. And what happens though is that the electron interacts with the ions within the copper conducting wire. So there is interaction between the electron and the ions in the copper wire, and so this causes it to slow down and also to change direction. But overall, with this constant force in that direction, it will cause the electron to maintain a movement going across like that. Alright, so it's 3 marks, so it's really important to show some sort of theory there, give an idea of that there's an acceleration, just doesn't continue to accelerate. There is this interaction between the electron and the ions, the negative and positive ions within mainly with the negative ions with the other electrons in the copper wire, and that causes it to slow down. There's a change of direction, but overall we get this drift velocity in that direction. Now we go on to this part over here. It says a copper rod is placed on 2 parallel horizontal conducting rails, PQ and SR, as shown below. The conducting rails are connected to a battery and a switch X. The rails in the copper rod are in a region of uniform magnetic field strength B. The magnetic field is normal to the plane of the conducting rods, as shown in the diagram. So we've got our magnetic field is down like that, and we have got our copper rod, which is as shown there. We've got our current is like that. So what's going to happen is this current is going to go through here, and it's going to be a current that direction and that direction. So you're going to have a current flow like that. The switch X is closed, and the current in the copper rod is I, and in the direction shown in the diagram. On the diagram, draw an arrow to show the direction of the force F on the copper rod. Okay, so using the right hand again, we put our fingers in the direction of the magnetic field, so that's down. The current is going into the board, so our thumb is going in to the page, and our palm of our hand will be pointing in that direction. So you're going to get a force like that. Okay. Then it says derive an expression in terms of B, L, M, and I for the initial acceleration of the copper rod. Now, we know that we have this formula over here. This formula applies because it's at 90 degrees, that's going to be 1. So we've got force is equal to BIL, like that. We also know that force is equal to mass times acceleration. So the acceleration is equal to force divided by your m. And therefore acceleration is again equal BIL divided by m. Like that. We then have the copper rod in B eventually moves with a constant speed V. When moving at this constant speed, the power supplied by the battery is equal to the rate at which work is done by the force F. Deduce that the power P supplied by the force F acting on the copper rod when it's moving at a constant speed V is given by this expression, power is equal to F times V. Well, let's just take this, that it's moving at a constant velocity, it's moving at a constant speed, so that's going to be moving with x over t. That's that time. So we have got two formulas here. We've got our power is equal to work over time. It's a rate of doing work. And we have our work that is being done is equal to Fx. So we're going to have, therefore, that the power is equal to Fx divided by t, and x over t is your velocity, so we get Fv will equal your power. Then it says use the expression in 1 and the data below to determine the speed v. So we have in this case over here, we have our power is equal to F times V. Now we know that the force is given by this formula over here. So because again, as I said, we're working at 90 degrees between the direction of the current and the magnetic field, we're therefore going to have power is equal to BIL times V, like that. Now we are given in this that your V is that. Now we know that power is equal to V times I. This is your potential difference now. So I've got VI is equal to BIL divided by V. So this current can cancel, so I'm going to get my voltage divided by BL is equal to my velocity. So this one is my velocity and this is my potential difference, the number of the volts. So I just put that in, obviously. So I've got 0.8 volts divided by B is 0.25 times by 0.6. And when we calculate that out, we get 5.3 meters per second to the negative 1.